Hello everyone, and welcome to this series about IPython notebook. This is part 8 and it's about sympy. Sympy is a symbolic mathematics library written completely in Python, so it doesn't have any dependencies. So you don't have to install any of the other SciPy ecosystem libraries to have sympy work. Sympy is completely written in Python and can work independently. To see what can we do with sympy, let's first import the library. The way you import it, we'll import everything within sympy. So from sympy, import star. Um, let's first take a look at a normal math equation. I'm just adding 3 to the square root of 3 using the math library of basic Python. This is the standard math library. So 3 plus the square root of 3 is 4.73. This is basically adding 3 to a rounded number of this of square 3 in a float context. The way to do the same thing within sympy, we will be adding 3 to square root of 3, and the result of that is square root of 3 plus 3. It's not a rounded number, so it will keep symbols the way they are. To express this in a more visual way, I will use initialize printing function. I'm passing use latex equals mathjax parameter. This is optional, but it resolves a bug in the current version. So I'll initialize printing, and I'll print the same expression again. And it's visually better now. It's square root of 3 plus 3 instead of square root of 3 plus 3 looking like this. So let's look at the square root of 8, for example. What it will do, it will try to simplify the your expression. In here, it get out 2 out of the square root, basically. So it's 2 times the square root of 2, and that's basically the square root of 8. Symbols. Symbols are like variables, so we can define symbols to include them in expressions. I'm defining x and y in here using symbols function. Then I'm defining an expression of x squared plus y squared. So you can write expressions using, you can include symbols within your expressions. This is another expression, x plus y to the power 3. Assumptions of symbols. Let's have a as a symbol. I can check if it's imaginary, and it returned nothing because it doesn't have any information about this symbol. I can assume that this is an integer, which b is an integer. So when I check if it's imaginary, it will return false because it knows that this number is not imaginary. C is a positive number, so I can check if it's imaginary, and it will if it's positive, and it will tell me yes, it's positive. And if it's imaginary, and it will tell me no, it's not, because it's a positive number. We can have imaginary numbers within our work or our expressions using capital I. So capital I to the power 2 is minus 2, basically. We can have rational numbers. So in here I have 1 over 3. Make sure you use capital R for rational, because that's a class. So in here I have 1 over 3. It didn't round the number to 0.33333. It evaluated the output as a rational number. I can do work with the rational numbers. I can add them together Can do all kinds of mathematical equations with them also. Numerical evaluation. I can use capital N to evaluate an expression. In here, I'm having the same expression of 1 over 3 plus 1 over 2, which is 5 over 6. And I'm evaluating that, and the result is 0.833333. I can control how many decimals do I want. So in here, I'm evaluating pi to 100 decimals. And this is how it will look. 3.14159 to 100 decimals. The other way to evaluate an expression is with the function evalf. That's evaluating an expression in float. And I can pass how many digits do I want, and that's it. It's 3.14159. Again to 100 decimals. Substitute. Let's have an expression. This is x to the power 2 plus 2x plus 1. I will substitute x with 1, and it will give me the result of that, 4. I can have a different expression. In here I have pi times x to the power 2. I will substitute x with 3, and it will tell me it's 9 pi. I can evaluate that. I'm using underscore in here. Underscore will always return your last input. So it will return 9 pi basically, and evaluate it. And that's 9 pi, which is 28.2. Factor and expand. Let's take a look at this expression. I have x plus y all to the power 2. I can expand this expression, and it will return x squared plus 2xy plus y squared. I can refactor that again, and it will return x plus y all to the power 2. Simplify. Simplify will try to simplify your expression. So in here I wrote this expression. It did try to simplify it in the beginning using simple thing. So in here I had 2x plus 1/3 times x, or 1 over 3 times x plus 4 divided by x. So what it did here, without simplifying this, it automatically added 2x plus 1 over 3x, and it returned 7 over 3x. I can simplify this using simplify function, and it will return 7 over 3 plus 4 over x. And that's much easier way to look at this equation. You can pass simplify come in handy also once you have a string equation or a string expression. So I can simplify a string expression, and it will return that expression back to me. I can have some geometry in here. I'm dividing sine x. It's sine x divided by cosine x. I can simplify that, and it's tan x. Apart and together. In here I have 1 over x to the power 2 plus 2x. I can have this apart, and it will split it. So I have minus 1 over 2x plus 4 plus 1 over 2x. I can put it back together, and it will return this. Sympy has a lot of functions to do calculus work. I will be just touching on the general things in here. The first thing I will be doing here, I have sine x, and I want to have the antiderivative for sine x. I will use the function diff for that, and I will pass the variable that I want to have the equation used as a variable basically. So I'm passing x in here, and a sine of x, the the differential of sine x is cosine x. In here, having a much more complicated equation, and it's uh, returning the differential of that fairly easily. I have log of 2 square plus 1 plus 2x, and it resolved that for me. I can have integral equations, so in here I'm saying integrate cosine x and it will return sine x, and I can keep the integral itself within um, my expression. So in here I'm having an integral equation of sine x dx from 0 to pi, and this is how you pass that. You pass your variable first, then your starting and ending points for your integration. You can evaluate that, and it will return 2.0, which is the integration of sine of x dx from 0 to pi. Sum. So in here I have a sigma from 1 to 10 for this equation of 1 over x squared plus 2x, and I can evaluate that using doit function, and that will evaluate this sum. Product. In here I have the same equation, but I'm evaluating the product for that, and I can evaluate that using the same thing, using doit. To have sum, use the sum function, and product, use the product function. Always pass the second argument as a tuple with your variable, then starting point and ending point. It's the same for product, a tuple with your variable, starting point and ending point. Solve will try to solve an expression assuming the expression is equal to 0. So in here I have 2x plus 1, and I will solve that, and it will tell me the result of that is minus half. And in here I have x to the power 2 minus 1. This has two answers because this is to the power 2, so minus 1 and 1. I can even solve systems of equations. And here I have two equations with two variables. So I have 2x plus y, and the other equation is 2y minus x is minus 5. And it's assuming all of those expressions are equal to 0. So I will solve that, and I will pass both variables inside a tuple, and I will pass my expressions in a list. So I'm passing both expressions in a list, and the second argument I'm passing my variables in a tuple, and it will return the value of x and y. So it basically solved this system of equations. Units. Units is part of the physics module in Sympy. It's pretty comprehensive. It has mechanics, it has quantum physics, it has all kinds of things, but I'm just touching on units here, so you get a sense of what you can do with units within Sympy. So I'm importing units as u from sympy.physics. I will execute that, and I will start with 5 times milligrams, u dot milligrams, and it's giving me the weight basically in kilograms. In here I can take a look at half an inch, and it's 0.127 meters. I can have nano, so this is not related to any specific unit, but it's a conversion basically, and it's telling me 1 nano is 1 times 10 to the power of minus 9, so 0.8 zeros then 1. It's really useful also to look at units. So in here I'm looking at watt, and it's telling me what is a watt or what's an ohm, for example. Converting from miles per hour to kilometers per hour. So what I'm doing in here, I'm dividing miles per hour and storing that in kilometer per hour, kmph. And I'm dividing miles per hour and storing that in mph, miles per hour. And I'm evaluating that, and result of dividing them is 1.6, which is how many kilometers in a mile, basically, because I'm dividing miles by kilometers per hour. So I can now look at what's 80 miles per hour, and it will tell me that's 128.7 kilometers per hour. So it's really handy once you have any kinds of units conversion. Plotting in SymPy. SymPy has a built-in plotting interface, and it basically interfaces with whatever system you have. It will prefer to go to Matplotlib, but if it doesn't have that, it will try to plot in text format. It will try to plot according to your what capabilities you have within your development environment. But make sure you have Matplotlib. That will make your plots much more clear to see. In here I'm plotting sine of 2 times sine of x to the power 3, and it's this interesting chart. So once you're plotting, you pass your expression. You use the function plot. You pass your expression as the first argument, and the second argument is a tuple, where you pass your variable, your starting point, which is 0, and your ending point, which is 10 in here. You can work with Numpy, Pandas, and Matplotlib, and I will show you now how to interface with something else within Numpy, Pandas, or Matplotlib. So in here I am defining a function. It has a SymPy expression. It takes one variable, and it basically substitute it in this expression, which is x to the power 2 plus square root of 3 times x minus 1 over 3. So I defined my function in here, and let me test it with the number 3, and that's the result of the number 3. I will import Numpy as NP, Pandas as PD, and Matplotlib .pyplot as PLT. These are almost standard, so try to use these short cuts for your libraries. I'm defining in here list 1, which is a NumPy array, and I'm defining a Pandas series and storing it in list 2. So I'll have 2 lists. One is a NumPy list, one is a Pandas list, to see how can we work with both of them. First, I will do the most simple thing. I will loop over my lists and time that and see what's the performance of doing it this way. Basically, I'm passing each item in my lists to that method. For the first one, it did that in 102 milliseconds. The second one, it did that in 104 milliseconds. These are really terrible results, actually. We will look at a more efficient way to do that. And I'm using, in here we're testing NumPy vectorize. So I can vectorize this, and I will pass the whole NumPy list to it. And in the second example, I'm applying it to my list in Pandas. I'm using apply function. Um, and the results are even worse than looping over the lists. Um, a really efficient way to do that is to have your expression in a variable and use a function named lamdify that will convert your expression into a lambda function. I'm storing my lambda function in lf. Now I will test it over the numpy list and the pandas series and see the numbers. In here you can see over the numpy array, it did that in 25 microseconds. And even with the pandas series, it did that in 440 microseconds, which are really much better numbers than these. In here, it did it in 1.1 seconds. Um, anyway, finally, let's plot this. I'm defining a figure and a subplot. I'm defining x values from -5 to 5, and then I'm passing those values to our lambda function lf, and then plotting it. And that's a function using our sympy expression to plot. Thank you for watching. This lesson is available open source on GitHub, and it's viewable on NB Viewer. The link to this document is available in the description box below. Feel free to use this whenever you're working with sympy. Thank you for watching, and I hope if you like this, you will subscribe to this channel and you will watch the next part of the series, which is the final part, and it's an exercise where I will be analyzing the Indian elections results of 2014. It's the largest elections in human history, I guess, with 814 eligible voters. So, thank you for watching.